Greetings of the day to all of you. A very warm welcome to another lecture on pulse width modulation techniques. In today's lecture, we are going to start our last module of the course, module 4. Right here, module 4. This is the last module. This module is mostly dedicated to a special type of pulse width modulation technique, which is called space vector pulse width modulation. The various contents of this module are, for example, we are going to learn about the concept of space vector. We are going to start with the basic concept of what is a space vector. In fact, we are going to cover that in today's lecture. Then space vector transformation. And that's also a part of lecture which I'm going to deliver today, space vector transformation. Then conventional space vector PWM, conventional space vector pulse width modulation, pulse width modulation, which is also in short form written as SVPWM, that is space vector pulse width modulation. And then we are also going to discuss equivalence of triangle comparison, equivalence of triangle comparison and space vector approaches to PWM. Equivalence of triangle comparison and space vector approach to pulse width modulation (PWM), and finally we are going to discuss space vector based advanced bus clamping techniques, SV based advanced bus clamping techniques. These are various topics which we will cover in this module, last module, module number 4. We will start with basic concept of space vector and then we will go for transformation, conventional space vector pulse width modulation. I will try to develop the concept of what is space vector pulse width modulation, SVPWM. Then we will try to compare SVPWM with triangle comparison PWM, which we have already discussed in module number 3. And finally, we are going to discuss some very special special types of space vector based pulse width modulation, which is called space vector advanced bus clamping techniques. These space vector based advanced bus clamping techniques are special techniques, PWM techniques, which are not possible with triangle comparison. Okay, so this is what we are going to cover in this module, module number 4. So therefore this module will comprise of a series of lectures, and in this series of lectures I will try to cover all these topics which I have enlisted here. So today we are going to start with the first topic of the module, that is basic concept of space vector. Basic concept of space vector. What is a space vector? What is its basic concept? How do we synthesize a space vector? How do we imagine a space vector? What does a space vector represent? Well, all of you have already studied AC machines in your BTech course. And in AC machine, you must have studied about three-phase induction machines. And in three-phase induction motors, for example, you know how what is the nature of a magnetic field. The three-phase stator winding of a three-phase induction motor is excited by balanced three-phase AC supply, which results in the flow of balanced three-phase currents in the three windings of the machine. And those three-phase balanced winding currents will produce rotating magnetic field or revolving magnetic field. So we can say that the rotating magnetic field, or what we call as a revolving magnetic field which is produced in a three-phase induction motor by application of three-phase sinusoidal currents to its three-phase windings by the flow of three-phase sinusoidal currents in its three-phase balanced windings. It produces rotating magnetic field, and this rotating magnetic field is analogous. It is analogous to what we call as a rotating space vector. Rotating space vector. So we have a machine, we give three-phase supply to it, three-phase balanced currents flow in its three-phase windings, and that produces a rotating magnetic field which, for example, is rotating in a counterclockwise direction at the speed which is determined by frequency of the supply, AC supply. In a similar way, we will try to develop the concept of space vector, and space vector is a reference phasor or reference vector which also rotates in the counterclockwise direction like this, and it traces a circular path. And this space vector will be basically representing three-phase sinusoidal voltages and three-phase sinusoidal currents. And this space vector will be analogous to your rotating magnetic field of induction machines. Let us start with pulsating single-phase induction machine. We know that a single-phase induction motor does not produce rotating magnetic field, but it produces a pulsating magnetic field. We will start from the basics. So, pulsating magnetic field produced by single-phase winding in a single-phase AC machine. I have a single-phase induction motor and it has a single-phase winding, and when this single-phase winding is excited by AC supply, single-phase AC source, AC voltage, it produces a pulsating magnetic field. So it is something like this. I will draw the elementary single-phase induction motor. Okay, it is like this. This is the stator of induction motor, single-phase induction motor, and this is the rotor, right? And on the stator we have distributed windings. Let me show you two or three windings, two or three coils on the top side and three coils on the bottom side. So this may be coil AA dash, coil BB dash, and coil CC dash, like this. Let us assume the current is coming out of these coils, so I will put dots here. And if current is coming out of these coils, obviously it will be going into these coils, so I will show crosses here. Dot means current is coming out of these coils, and cross means it's going into this coil. For example, when current is flowing in this coil, it is flowing out of this plane of the board, and it is flowing. This is A dash, this is one coil side, this another coil side. In this, so it is something like this. Coil is like this. In this coil, the current, say for example, this is A dash. Current is flowing out, so current is flowing out. Then it is in A dash, it is flowing in, so it is flowing into this. So here it is flowing out of the plane of the board, in your case plane of your paper, and here it is going into the plane of the board or plane of paper. So therefore currents shown by dots means currents are coming out, and currents shown by crosses means currents are going in there into the plane. Okay. Now these currents, single phase, AC currents, they will produce a magnetic field, and use the right hand rule. This is the right hand rule. Right hand rule says that the axis or direction of magnetic field will be like this. Just curl these fingers. Okay. I am putting my fingers like this. So that means the current is, in these top conductors, the current is coming out, and in bottom conductors going into. So the fingers means that the currents are coming out of these coil sides, these conductors, and then they are going into these coil sides. Oh, okay. If this is the direction of current coming out of here and going into these conductors, then the thumb will show the direction of magnetic axis or direction of magnetic field. So this will be the direction of magnetic field. So this is magnetic field axis, B axis. Okay. Now you will find magnetic field will be at its maximum here. Then as you go, you move along this air gap, along this rotor. So as you move towards these coils, the strength of magnetic field will reduce, and when you reach here, magnetic field will be 0. And if you move to the other side, the magnetic field will be negative maximum here, and then when you reach here, it will be 0. Then again you reach here, it is maximum here. So magnetic field is maximum along this axis and along this axis, and it is 0 along these axes. Okay. So therefore, if I take at any instant of time, let us take an angle, space angle, theta AE. A means air gap. This is the air gap angle. For example, this is the magnetic field axis. Magnetic field is maximum here. What will be magnetic field here? There will be some magnetic field here as well. The angle of this axis with respect to this reference axis, that is called air gap angle. Theta AE. A stands for air gap, E stands for electrical. Now as far as this magnetic field is produced by this current flowing in these windings, this magnetic field will not be purely sinusoidal. As we already know, magnetic field is never sinusoidal. There are always some space harmonics associated with the magnetic field. Let us assume that let us ignore the space harmonics and take only the fundamental component of magnetic field, or fundamental component of, what we call as fundamental component of MMF. So therefore, I will write here fundamental component of R phase MMF. I am writing here R phase. I take this phase as R phase. It is a single phase machine, so there is only one phase. So let me call this phase as R phase. So what is the fundamental component of R phase? MMF. MMF produced by the currents flowing in these windings. Current flowing in this winding, AC current, sinusoidal AC current flowing in these windings will produce MMF. And what is the fundamental component of that MMF? The fundamental component of that MMF is given by, say, FR1 equal to KIR cos theta AE. Actually, the MMF is directly proportional to current flowing in the winding. What is the current flowing in R phase winding? IR. So if you, K is the constant of proportionality. So FR1 is KIR, and then this cos of this air gap angle cos theta AE. For example, you may be finding a fundamental component of MMF somewhere here. So this, when you find fundamental component of MMF along this axis here, so you have to take this space angle, air gap angle also into consideration. You have to multiply it with cos theta AE. So R stands for, F stands for MMF, R stands for R phase, and 1 stands for fundamental. So this FR1 means fundamental component of MMF produced by the current flowing in the R phase. It's given by KIR cos theta AE. And what is IR? We know that in single phase induction motor, sinusoidal current is flowing in the winding. So IR is given by IM cos omega ET, where this omega E is the frequency of supply. It may be 50 hertz or it may be 60 hertz. So therefore, what is FR1? Fundamental component of R phase MMF, it is K into IR. IR is IM cos omega ET into cos theta AE. Okay. So let us try to simplify this. So this can also be written as, here I will write FR1 K IM. Let me write cos theta AE first and then cos omega ET. Okay. So FR1 will be equal to FM into cos of theta AE into cos of omega ET, where what is this Fm? Fm is the peak value of MMF. So it is given by KIM. It is given by KIM. So I am replacing this KIM term by Fm. Fine. If you use trigonometric identity, you will find fundamental component of MMF produced by current flowing in the winding of sinusoidal current flowing in the winding of a single phase induction motor. It is given by F max by 2. You can call this F max here. F max. It is F max by 2 times cos of theta AE minus omega ET plus cos of theta AE plus omega ET. What is the origin of this equation? My FR1 is basically F max cos theta AE into cos omega ET. So this can also be written as F max by 2 times cos of theta AE minus omega ET plus cos of theta AE plus omega ET. It is because if you expand this expression FR1, it is F max by 2. So this is cos of A minus B, and cos of A minus B trigonometric identity is equal to cos A cos B plus sin A sin B. So this is cos theta AE into cos B, that's cos omega AT, minus sin A sin B, that is sin theta AE into sin omega AT. Okay, plus similarly this identity cos of A plus B is cos A cos B minus sin A sin B. So this is cos A cos B minus sin, here it is plus, minus sin A sin B. I'll repeat, cos of A minus B is cos A cos B plus sin A sin B, and cos of A plus B is cos A cos B minus sin A sin B. Now this sin theta AE sin omega AT and minus sin theta AE sin omega AT, they add up to 0. So what are we left with? We are left with F max by 2 cos theta E cos omega AT plus cos theta E cos omega AT. So this is 2 times cos theta AE cos omega AT. Now this 2 and 2 cancels, so this comes out to be F max into cos theta AE cos omega AT. So this is original equation, because originally what was my FR1 equal to? It was F max cos theta AE cos omega AT. So it has given me the same result. That means if I write this expression as F max by 2 times cos theta AE minus omega AT plus cos of theta AE plus omega AT and expand it, it goes back, it gives me the same value as the original value. Okay, so fine. So therefore my FR1, I will write again, is equal to F max by 2 times cos of theta AE minus omega ET plus cos of theta AE plus omega ET. Is it okay? Yeah. Now here, this means your magnetic field or MMF produced by current flowing in the single phase winding of a single phase induction motor, it causes the MMF to rotate, say, in clockwise direction. Because what is theta AE? It's the air gap angle, and this theta AE is changing. I mean, it's like this. So that means this component of MMF, it represents an MMF which is revolving in clockwise direction. And here it is theta E plus omega ET. So this is another revolving component of pulsating magnetic field which revolves in counterclockwise direction. Okay. So therefore, we already know that the magnetic field produced by the single phase winding of a single phase induction motor is not rotating one, it is pulsating. I mean, this may be North Pole, this may be South Pole. After some time, this becomes North Pole, this becomes South Pole. It's not rotating, it's pulsating like this. But this pulsating magnetic field can be resolved into two revolving magnetic fields, one revolving in the clockwise direction given by this equation, and another revolving in counterclockwise direction given by this equation. So therefore, we can write that fundamental component of MMF produced by current flowing in a single phase induction motor winding, it is equal to Fr plus Fr minus, where Fr plus is the revolving magnetic field. It's the magnetic field revolving, it's the component of magnetic field or component of MMF which is revolving in the clockwise direction, and Fr minus is the component of MMF which is revolving in the counterclockwise direction. If you add these revolving magnetic fields together, it will again give rise to pulsating magnetic field. So this means pulsating magnetic field can be resolved into two revolving magnetic fields, two revolving components. Okay, what are those revolving components? One revolving in clockwise direction, which is given by F max by 2 times cos of theta AE minus omega AT, or it is represented by Fr plus, and other in counterclockwise direction, which is given by this equation, F max by 2 times cos of theta AE plus omega AT, and it is represented by Fr minus. So I am sure you already know this. You must have been taught this by your electrical machines course, electrical machines teacher in your electrical machines course while studying single phase induction motors. We know that a single phase induction motor has only one winding and is excited by single phase AC. The single phase sinusoidal currents flowing in the winding, it's responsible for producing the pulsating magnetic field, and that pulsating magnetic field can be resolved into two components, revolving components, one revolving in clockwise direction, Fr plus, and another revolving in counterclockwise direction, that is Fr minus. So that is about pulsating magnetic field produced by single phase induction motor, single phase winding in a single phase induction motor. Now let us quickly go to a three-phase induction motor. What type of magnetic field does a three-phase induction motor produce? It does not produce pulsating magnetic field. It produces a revolving or rotating magnetic field. So I will write here rotating magnetic field produced by three-phase winding in a three-phase AC machine. When I say three-phase AC machine, it exclusively means three-phase induction machine, three-phase induction motor. So the magnetic field will be produced here by three-phase windings, because in three-phase induction motor we don't have single-phase winding, we have three-phase windings, and that three-phase winding is excited by three-phase AC supply, and that results in the flow of balanced three-phase sinusoidal currents in the three-phase windings, which are 120 degrees displaced in space with respect to each other, and that will result in the production of rotating magnetic field. Let us see how. For that purpose, we will draw the elementary three-phase induction motor model again. This is again rotor, this is stator. Now we have R phase winding, for example. This is R phase winding comprising of three coils, having three coil sides here and three coil sides here. In these three coil sides, current is flowing as shown by dots. Dots means coming out, and in these three coil sides, current is flowing in the direction shown by crosses, means into the plane. So this is R phase winding. What about Y phase winding? Y phase winding will be here. This is R, R dash. Y phase winding will be like this, Y, Y dash. And this is the direction of current. And then we have third winding, which is also, these two windings are 120 degrees phase displaced. For example, if this is R phase winding, this will be Y phase winding, 120 degree phase displaced. Then you have third winding, B phase winding. That's again 120 degrees displaced from, this winding. Okay, so that B phase winding can be shown here, B dash. So current as shown by dots, current as shown by crosses. Now instead of having one magnetic field axis, here I will have three magnetic field axes. What is the current flowing in R phase winding? It is like this. Apply this right hand rule. So current is coming out of these conductors and then it is flowing into these conductors. So my fingers will show direction of current coming out and going in, and this is the axis of R phase magnetic field. So this is R phase magnetic field. Of course, BR you can say. And in Y phase winding, current is coming out here and it is going into. So apply right hand rule. It's like this, coming out of these conductors, going into these conductors. So direction of magnetic field is shown by my thumb. So this will be Y phase magnetic field. Let's call this BY. And then what about B phase magnetic field? B phase magnetic field, let me change the direction of currents. Just dot, and these are crosses. Current is coming out of these conductors and it is going into these conductors. So that's my fingers are showing, and my thumb shows the direction of the axis of magnetic field. So this is R, B, R, Y, and this is B. So BB. So therefore, now we have three axes. This is the axis of magnetic field produced by the current flowing in R phase winding. This is the axis of magnetic field produced by current flowing in Y phase winding. And this is the axis of magnetic field created by current flowing in B phase winding. Okay. Now, if you take these windings, individually, the current in R phase winding will produce a pulsating magnetic field. The current in Y phase winding will also produce a pulsating magnetic field, and current in B phase winding will also produce a pulsating magnetic field. Let us write equations for those pulsating magnetic fields. So, pulsating magnetic fields or pulsating MMFs produced by individual windings, produced by each winding, that's R phase winding, Y phase winding, and B phase winding, R. They are given by, let us write, fundamental component of pulsating magnetic field produced by current flowing in R phase winding, so FR1. So same equation, it is K into IR cos of theta AE, same which we have just few moments back written for single phase induction motor. Now, in addition to R phase winding, we have Y phase winding also. That will also produce a pulsating magnetic field whose fundamental component is pulsating MMF produced by Y phase winding, whose fundamental component is given by K into IY cos of theta AE minus 120 degrees, because Y phase winding is displaced with respect to R phase winding in space by 120 degrees. So I have to write here minus 120 degrees. Okay. Similarly, the current flowing in B phase winding will also produce MMF, and the fundamental component of B phase MMF is given by K into IB cos of theta AE minus 240 degrees, or theta AE plus 120 degrees, because B phase winding is displaced with respect to R phase winding by 240 degrees. Okay. Now what are IR, IY, IB? IR, IY, IB are the currents flowing in the three phase windings. The current flowing in R phase winding, IR, we know it is equal to IM cos of omega ET. Current flowing in Y phase winding is IY, which is given by IM cos of omega ET minus 120 degrees. So current in Y phase winding is out of phase with respect to current in R phase winding in time by 120 degrees. Okay, and similarly IB is equal to IM cos of omega ET minus 240 degrees. theta AE are space angles and omega ET are electrical angles. Okay, so therefore if I write FR1 is equal to K into IR into cos theta AE. So put IR here. So it is K into cos, okay, K into IM. Let us write cos theta AE first, this term first, and then cos omega ET, right? What about FY1? FY1 will be equal to K into, let me write cos, K into IM, let me write cosine term first, this cos theta AE minus 120 degrees, and then current term is cos of into cos of omega ET minus 120 degrees. Fine. Similarly, FB1 is equal to K into IM. I will write this term first, cos of theta AE minus 240 degrees into this term, cos of omega ET minus 240 degrees. Fine. So I have three equations now. If you remember just few moments back when we were discussing pulsating magnetic field produced by single phase winding in a single phase induction motor, this FR1 we had written as KIM by 2 or F max by 2 cos of theta AE minus omega ET plus cos of theta AE plus omega ET. That's, we resolved this pulsating MMF into two revolving components, one revolving in clockwise direction and another in anti-clockwise direction. So this can be done for a three-phase induction motor also, individually for all the three windings. So therefore FR1 can be written as, what is K into IM? It is F max. Let me first of all write F max into cos of theta AE into cos of omega ET. This is this equation. Then let us take second equation. Fy1 is equal to K into IM. It's again F max into cos of theta AE minus 120 degrees into cos of omega ET minus 120 degrees. Let us do it for B phase. So fundamental component of B phase MMF FB1 is equal to K into IM is F max again, cos of theta AE minus 240 degrees into cos of omega ET minus 240 degrees. Fine. Let us resolve each pulsating MMF of all the three phase windings into revolving components as we have done for single phase induction motor. So therefore I can write FR1 equal to F max by 2 into cos of theta AE minus cos of theta AE minus omega ET plus cos of theta AE plus omega ET. Okay, this is FR1. What about FY1? FY1 is also F max by 2 into cos of theta AE minus omega ET. This is the component which is flowing, revolving in the clockwise direction, plus what is the component which is revolving in anti-clockwise direction? That is cos of cos of theta AE plus omega ET. The minus 120 degrees minus 120 degrees is minus 240 degrees. That is also equal to 120 degrees. Okay. So this is this pulsating magnetic field or pulsating MMF I am resolving into two components, same way as I have done for single phase induction motor. This is the clockwise component and this is the anti-clockwise rotating component. Here I can write this as FR plus and this as FR minus, FR plus and this as FR minus. Clockwise rotating component, anti-clockwise rotating component. Similarly, this as Fy plus and Fy minus. This component is the revolving component, revolving in clockwise direction, and this component of MMF or magnetic field is the revolving component which is revolving in the counterclockwise direction. Similarly, FB1 is equal to F max by 2 into cos of theta AE minus omega ET plus cos of theta AE plus omega ET minus 240 minus 2. See, instead of writing minus 240 degrees, we could write plus 120 degrees also. Here also I could write plus 120 degrees. So what is 120 plus 120? 120 plus 120 is 240 degrees. So it is plus 240 degrees. Okay. So this is clockwise revolving component FB plus, and this is anti-clockwise revolving component FB minus. Right? Fine. So therefore, what is the total magnetic field? Okay. Total magnetic field in induction motor is fundamental MMF produced by R phase winding plus fundamental MMF produced by Y phase winding plus fundamental MMF produced by B phase winding. So therefore I can write F1 average is equal to FR1 plus FY1 plus FB1, which is equal to, what is FR1? So in terms of, components, these are pulsating magnetic fields. All three are pulsating magnetic fields. But we have already resolved them into clockwise and anti-clockwise rotating components. So this is the clockwise revolving component. So I can write it is equal to FR plus this is the counterclockwise revolving component, FR minus. Similarly, plus Fy plus Fy minus. So plus FB plus FB minus, right? So I can also write it like this. I can also write F1 average is equal to, let me take these positive components, we segregate clockwise rotating components FR plus Fy plus FB plus, and then counterclockwise rotating components. I am, segregating them. Clockwise rotating components I am putting together, and counterclockwise rotating components I am putting together. Fr minus plus Fy minus plus Fb minus. So therefore my total MMF or total magnetic field in the air gap is equal to Fr plus Fi plus Fb plus Fr minus Fy minus Fb minus. As far as these counterclockwise revolving MMFs are concerned, my Fr minus is cos of theta AE plus omega AT plus Fi minus is cos of theta AE plus omega AT plus 120 degrees plus Fb plus is cos of theta AE plus omega T plus 240 degrees. If you add these and expand them using trigonometric identity cos of A plus B, okay, the sum of the three will add up to 0. So therefore Fr minus plus Fy minus plus Fb minus, this will add up to 0. You can try it yourself. It's very simple. It's cos of A plus B plus cos of A plus B plus cos of A plus B. You expand them, add them up, and this addition will be equal to 0. So therefore, what are we left with? We are left with, therefore, F1 air gap MMF is equal to only this clockwise revolving magnetic fields. Fr plus Fy plus Fb plus. What is Fr plus? Fr plus F max by 2 cos of theta E minus omega it plus Fy plus is cos of same term F max by 2 cos of theta E minus omega t, and Fb plus is also same term F max by 2 cos of theta E minus omega t. So we can write it is equal to 3 times Fr plus. Okay, or it can be written as F1 can be written as, it is F max by 2 cos of this plus this. When you add them up, it will be 3 by 2, 3 F max by 2 into cos of theta AE minus omega ET. So you have only one rotating component now. Okay. So and the three clockwise rotating components of pulsating magnetic field, they will add up 3f max by 2 cos of theta ae minus omega et. So therefore it will produce, this equation tells us that the three-phase winding, when it is excited by three-phase supply and three-phase balance, currents are flowing, sinusoidal currents are flowing in three-phase winding of induction motor, it gives a revolving magnetic field. Okay, it has only one component, one revolving magnetic field, because the other counterclockwise component has added up to 0. So this is rotating MMF. And rotating MMF gives rise to rotating magnetic field. Rotating magnetic field. Okay, so therefore mathematically we have proven that three-phase winding in a three-phase induction motor, when excited by a three-phase sinusoidal supply, and when three-phase sinusoidal currents are flowing in this three-phase winding, it produces a rotating magnetic field. So it can be shown like this. I have three-phase windings. This is phase R. For example, this is phase Y and this is phase B. Okay, the three-phase windings give rise to a rotating magnetic field or rotating MMF tau, which is rotating, say for example, in counterclockwise direction. Although a few moments back I have told you clockwise, it can be clockwise or anti-clockwise. So we generally take the convention of counterclockwise direction. Okay, so when currents are flowing in three-phase windings, say IR, IY and IB, the three-phase currents flowing in three-phase windings of an induction motor produces a revolving magnetic field, which is revolving at a speed determined by frequency of the currents or frequency of the supply. Okay, so this is the revolving magnetic field. Now, can we transform this? This is three-phase winding and three-phase quantities are there. For easier computations, can I transform a three-phase system into a two-phase system? This is three-phase stationary reference frame. IR, IY, IB, these are all, these frames, the winding, R winding, Y winding, B winding, they are stationary, they are not rotating. Rotor is rotating. So this frame is called three-phase stationary reference frame. Can I transform this three-phase stationary reference frame into two-phase stationary reference frame, which will also give me a rotating magnetic field like this? Answer to that question is yes. Now, I am going to discuss with you, transformation from three-phase stationary reference frame to two-phase stationary reference frame. Two-phase stationary reference frame. For ease of computations, instead of having three-phase stationary reference frame, we can work in two-phase stationary reference frame, or in other words, we can now consider equivalent two-phase windings. Originally we have three-phase winding, and now we can transform that three-phase winding into equivalent two-phase winding. So that can be done like this. For example, this is original three-phase winding, R phase, this is Y phase, and this is B phase. And it produces a revolving magnetic field tau, which is revolving in counterclockwise direction. It's of constant magnitude and revolving at speed determined by the speed of the frequency of the supply. Now this three-phase stationary reference frame or three-phase winding can be transformed into two-phase stationary reference frame or equivalent two-phase winding like this. So instead of working with three-phase windings, we can work with only two-phase winding. This winding is called alpha axis and this winding is called beta winding. This alpha axis, beta axis. Here you have R axis, Y axis, B axis. Here you have only two axes, alpha and beta, and these alpha and beta windings are 90 degrees in space with respect to each other, whereas in three-phase stationary reference frame you have three windings, R, Y and B, which are 120 degrees with respect to each other in space. But in equivalent two-phase windings, equivalent, two-phase stationary reference frame, this three-phase winding is transformed into two-phase winding, and the two-phase windings alpha and beta, they are 90 degrees in space with each other, and they carry currents I alpha and I beta, which are displaced in time with respect to each other by 90 degrees. Here we have three currents IR, IY, IB, which are displaced in time by 120 degrees. And in two-phase winding, equivalent two-phase winding, we have two currents I alpha and I beta, which are displaced in time by 90 degrees. Now the question is how to transform this three-phase winding into equivalent two-phase winding, or how to transform three-phase stationary reference frame into two-phase stationary reference frame. This two-phase stationary reference frame will also produce rotating magnetic field, same rotating magnetic field. Okay. Now for this purpose, if you find the MMF along Y alpha axis, I can write Ni alpha. I alpha is the current along alpha, current carried by alpha axis, multiplied by number of turns, it gives MMF along alpha axis. Okay, so it is equal to, if you see the three-phase windings, in three-phase winding, IR is flowing in R phase winding, and you can see this IR, R phase winding is same as alpha winding. Okay, this is alpha and this is beta. R phase winding is aligned along alpha axis, so it is equal to, I would like to say it is N into IR into cos 0 degree, because R phase winding is aligned along alpha axis, so it is cos 0, plus what is the component of Y phase MMF on alpha axis? That is given by N into IY cos 120 degrees, because Y phase axis is at 120 degrees with respect to alpha axis or with respect to R axis. So its component along alpha axis is N into IY cos 120 degrees. And what is the component of MMF produced by current in B phase winding along alpha axis? That is plus N into IB cos 120 plus 120 is 240 degrees, because this is 120 plus 120, 240 degrees. Right? So this is MMF along alpha axis. What about MMF along beta axis? Ni beta. That is equal to, along this beta axis, there is no contribution of R phase MMF, because this R phase and beta axis, they are at 90 degrees, and cos 90 degrees is 0. So R phase current or R phase MMF has no component along beta axis. Whereas Y phase and B phase MMFs have their components along beta axis, which is this axis or this axis. So then I can write NIY. What is this angle between beta and Y? This is 30 degrees. So this is NIY cos 30 degrees plus, and what is this angle between these two windings? It is 120 degrees. And what is total angle between B phase winding and beta axis? 120 plus 30 is 150 degrees plus NIB cos 150 degrees. So this is the component of MMF along beta axis because of MMF, in B axis. So this is how we find equivalent MMFs in alpha beta equivalent two-phase winding in terms of, MMFs of three-phase winding. This is called transformation. And we are now transforming a three-phase reference frame into two-phase reference frame. That is RYB reference frame into alpha beta reference frame. Or we are transforming three-phase winding into equivalent two-phase winding. And these are the equations we have to use. So therefore, in terms of currents, I can write I alpha is equal to IR, cos 0 is 1, so it's IR plus IY. What is cos 120 degrees? Cos 120 degrees is minus 1 by 2 plus IB, cos 240 degrees is also minus 1 by 2. And similarly, I beta is equal to IY. What is cos 30 degrees? It is root 3 by 2 plus IB. What is cos 150 degrees? Minus root 3 by 2. Fine. So therefore, we can write like this. I can write I alpha is equal to IR. So this is minus 1 by 2 IY minus 1 by 2 IB. Minus 1 by 2 IB. Okay. So I can take minus 1 by 2 out, or I can write plus 1 by 2 into minus Iy minus Ib. Okay, in a balanced three-phase system, IR plus Iy plus Ib is equal to 0. So therefore, what is IR? IR is equal to minus Iy minus Ib. So therefore, minus Iy minus Ib is equal to IR. I can put it here. Therefore, I alpha is equal to IR plus 1 by 2 into minus Iy minus Ib, that is equal to IR. So IR. So this means I alpha is equal to 2 plus 1. So this is 3 by 2 IR. This is I alpha. Equivalent current along alpha axis in terms of currents in three-phase windings. In terms of currents in three-phase windings, 3 by 2 IR. What about I beta? I beta is root 3 by 2 Iy. So I can take root 3 by 2 outside. So it is Iy minus Ib. Iy minus, if I take root 3 by 2 outside, so it is Iy minus Ib. So therefore I have got two very important equations. When I transform three-phase winding into equivalent two-phase winding, or when I transform three-phase stationary reference frame into two-phase stationary reference frame, in the stationary two-phase reference frame, I get two currents, one current carried by alpha axis and another by beta axis. I alpha is given by 3 by 2 IR and I beta is given by root 3 by 2 times Iy minus Ib. So this is how we transform a three-phase winding into equivalent two-phase winding. And when these currents 3 by 2 IR is flowing along alpha axis and root 3 by 2 Iy minus Ib is flowing along beta axis, it will produce a rotating magnetic field just like a three-phase winding carrying currents IR, Iy and Ib produce rotating magnetic field. Okay, so this is how this transformation is done. So I will write these equations again. I will again write I alpha is equal to 3 by 2 IR and I beta is equal to root 3 by 2 times Iy minus Ib. So in matrix form, if I put these equations in matrix form, it's like this. I alpha, I beta is equal to matrix here, and then IR, Iy and Ib. So first component will be 3 by 2, then 0, 0, and second component will be 0, root 3 by 2 and minus root 3 by 2. Now we can see I alpha is 3 by 2 IR plus 0, that's 3 by 2 IR. And I beta is 0 plus root 3 by 2 Iy minus root 3 by 2 Ib, that's root 3 by 2 times Iy minus Ib. So this is how we put it in matrix form. This is currents. What about voltages? What about voltages? Transformation of three-phase voltages. This was transformation of currents. Now if you take transformation of three-phase voltages into equivalent two-phase voltages, so in a similar way, I will write the equation V alpha is equal to Vrn phase voltage, Vrn plus Vyn cos 120 degrees plus Vbn cos 240 degrees, and V beta will be equal to Vyn cos 30 degrees plus Vyn cos 30 degrees plus Vbn cos 150 degrees. We have written these equations for currents a few moments back, and we can write for voltages also. Okay, and V alpha will be given by Vrn plus, this is minus 1 by 2 Vyn minus 1 by 2 Vbn. That is equal to 3 by 2 Vrn. Just like I alpha is 3 by 2 IR, V alpha is also equal to 3 by 2 Vrn. Okay, and V beta is equal to, this is root 3 by 2, this is minus root 3 by 2. If you take root 3 by 2 outside, it's Vyn minus Vbn. So therefore, I can in nutshell write in terms of voltages. I have two voltages, V alpha equivalent two-phase voltages. V alpha is equal to 3 by 2 Vrn, and V beta equal to root 3 by 2 times Vyn minus Vbn. And you must remember that the sum of the three currents IR plus IY plus IB is equal to 0, and the sum of three phase voltages Vrn plus Vyn plus Vbn is also equal to 0. So this gives x plus y plus z equal to 0, and this equation is equation of plane, equation of space. So therefore, three-phase voltages, basically, you have three-phase voltages. This is R axis, this is Y axis, this is B axis. These three-phase voltages produce a rotating magnetic field in a space. Or equivalently, if you take, two equivalent two-phase winding or a two-phase stationary reference frame, alpha and beta, that also produces rotating magnetic field or rotating MMF in space. So this is equation of space. Okay. So this forms fundamentals of our, space vector. What is space vector? I have not yet come to that. We are just discussing, how a rotating magnetic field is produced by a three-phase induction motor, then pulsating magnetic field first produced by single-phase induction motor, and then how a three-phase induction motor produces rotating magnetic field, and then we transform three-phase winding into equivalent two-phase winding, or we transform three-phase stationary reference frame into equivalent two-phase stationary reference frame, RYB into alpha beta, and we derived the equations for current in alpha axis and current in beta axis, that's I alpha, I beta, in terms of currents in the three-phase windings IR, IY, IB, or voltage along alpha axis V alpha and voltage along beta axis V beta in terms of voltages in VR, VY and VB. Okay, this is how transformation is done. These are the transformation equations. Now let us go to our inverter, three-phase voltage PWM voltage source inverter. I will write here three-phase two-level voltage source inverter. Let me draw the power circuit diagram of a three-phase two-level voltage source inverter. There is a lot of renovation work going on in our laboratories. I am recording this lecture in my office, and just in the adjacent lab, renovation work is going on. That's why you are listening to the noise of the machines. So we have to bear with it. So these are my switches, say S1, S3, IGBT switches, S1, S3, S5, top switches, and bottom switches are S2, S4 and S6. And this is phase R. Y, it is connected to midpoint of phase leg R. Y is connected to midpoint of phase leg B, and Y, and B is connected to midpoint of phase leg B. And I may have a three-phase load like this. Connected like this, and this is the neutral of the load. Okay, and here I have DC buses. I have DC bus, and these are DC bus capacitors with voltage plus, this is VDC by 2 and VDC by 2, and this is the midpoint of your DC bus. Now we know that each phase leg produces a pole voltage. For example, if top switch of phase leg R is on, the pole voltage VRO is plus VDC by 2, and if bottom switch S4 is on, it is equal to minus VDC by 2. So VRO pole voltage is equal, it may be plus minus VDC by 2. Plus minus VDC by 2 means if top switch S1 is on, VRO is plus VDC by 2, and if bottom switch S4 is on, it is equal to minus VDC by 2. VYO is also equal to plus minus VDC by 2, and VBO is also equal to plus minus VDC by 2. So these are our pole voltages, 3 pole voltages. Now, can I write, now inverter produces 3-phase AC output. So it produces voltage VRN, voltage of phase R with respect to neutral of the load. It produces voltage VYN and it produces voltage VBN. These are 3-phase voltages. Now, instead of writing equations for 3-phase voltages, I will transform this 3-phase into equivalent 2-phase. That is, I will not work in 3-phase stationary reference frame. I would like to work in 2-phase stationary reference frame, because that will later on make my computations easy. So in 2-phase stationary reference frame, or in terms of 2-phase stationary reference frame, that is alpha beta reference frame. What is my V alpha in terms of these phase voltages VRN, VYN, VBN? You have studied, if you study, you have already studied 3-phase 6-step voltage source inverter, and if you go back to that and you transform 3-phase voltages into equivalent 2-phase voltages, you transform 3-phase reference frame into 2-phase reference frame, alpha beta reference frame, V alpha will be given by this relation, 3/2 VRN. It will be given by 3/2 times VRN. Okay, and that is equal to 3/2 times, if you remember in one of the previous classes, this phase voltage VRN can be written in terms of line voltage as 1/3 times VRY minus VBR. You must have already studied it in 6-step voltage source inverter. This phase voltage in terms of line voltage, we have already discussed it in module 3, last couple of lectures of module 3. VRN is 1/3 times VRY minus VBR. Now this 3 and 3 goes, that means V alpha will be equal to 1/2 times VRY minus VBR. So this is in terms of line voltages. But what do I have? I have pole voltages. Can I represent this voltage along alpha axis in terms of pole voltages? Answer is yes. So it's 1/2 times, what is VRY? It's line voltage VRY is equal to pole voltage VRO minus pole voltage VYO. So it is VRO minus VYO, minus VBR is VBO minus VRO. Minus into minus is plus, plus VRO. Okay, fine. So therefore it can also be written as V alpha, therefore can be written as V alpha is equal to 1/2 times, I have VRO plus VRO, that is 2 times VRO minus VYO minus VBO. This is one very important equation. You have to remember it at the tip of your tongue. This is how we represent, V alpha, equivalent alpha axis voltage in terms of pole voltages, 3-phase pole voltages, VRO, VYO, and VBO. We are basically transforming 3-phase, quantities to 2-phase quantities, or we are transforming from 3-phase reference frame to 2-phase reference frame, alpha beta reference frame. And for that, V alpha is given by 1/2 times VRO minus VYO minus VBO in terms of pole voltages. And what about V beta? Remember that V beta is given by √3/2 times VYN minus VBN. It is √3/2 times phase voltage VYN minus phase voltage VBN. These phase voltages are equal to pole voltages, we already know. So therefore V beta will be equal to √3/2 times VYO minus VBO. This is another equation which you have to remember at the tip of your tongue. Okay, so these are our 2 equations. So therefore, if you want to work in alpha beta stationary reference frame, you must know 2 voltages, V alpha and V beta. And in terms of pole voltages, 3-phase pole voltages, V alpha is 1/2 times 2 VRO minus VYO minus VBO, and V beta is √3/2 times VYO minus VBO. Fine. Now let us see how many switching states I have in my inverter. So I will write here inverter switching states. Each phase leg has two switching states. For example, either top switch is on or bottom switch is on. Similarly, this leg also has two states. Top switch is on, bottom switch is on. This leg also has two states, switching states. One switching state when top switch is on and one switching state when bottom switch is on. So 2 plus 2 plus 2 is 6. Does it mean that my inverter has 6 switching states? No, it has 8 switching states. Another switching state is when all the 3 top switches are on. That is 7th state, and 8th state is when all the bottom switches are on. We have already discussed it in triangle comparison based PWM techniques. So therefore I have 2 raised power 3 switching states, which is 8 switching states. 8 switching states. And what are those 8 switching states? Let us write top switches only: S1, S3, S5. S1, S3, S5. Either all the top 3 switches are off, 0, 0, 0. Means all the 3 top switches are off. When all the 3 top switches are off, at that time all the 3 bottom switches will be on. Second is 0, 0, 1. Then 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0 and 1, 1, 1. These are 1, 2, 3, 4, 5, 6, 7, 8. 8 switching states of my inverter. Now this 0, 0, 0 I can write as minus, minus, minus. We will be following this notation. Plus means top switch is on and minus means bottom switch is on. When I write minus, 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 it means all the 3 bottom switches S2, S4, S6 are on. Second switching state is 0, 0, 1. That is minus, minus, plus. Minus, minus, plus. It means in phase leg R, bottom switch S4 is on. In phase leg Y, bottom switch S6 is on. But in phase leg B, top switch S5 is on. So therefore S1 and S3 are off and S5 is on. Next switching state is 0, 1, 0. Minus, plus, this means S1 is off, S3 is on, S5 is on. In other words, S4 is on, S3 is on and S2 is on. 2 bottom switches and 1 top switch is on. Then 0, 1, 1. Minus, plus, then 1, 0, 0. Plus, minus, minus. Then 1, 0, 1. Plus, minus, 1, 1, 0. Plus, plus, 1, 1, 1. Plus. So these are my 8 switching states. 1, 2, 3, 4, 5, 6, 7, 8. There is a lot of disturbance around. 0 switching state. So I have 8 switching states, out of which minus, minus, minus and plus, plus, plus. Let's hold on. Minus, minus, minus means all the 3 bottom switches are on. Remember, we have already discussed it in triangle comparison based PWM techniques. When all the 3 bottom switches are on, your load is shorted by through these bottom switches. Your load is not connected to the source, AC side, DC side, input source. It is shorted. So a sort of freewheeling is taking place here. Okay, when switching state, if it is minus minus minus, it means all the three bottom switches are on, and your load gets shorted through these switches. It's not connected to source, so there is no transfer of energy from source to load. There is freewheeling. So that's why this state is called zero switching state. Similarly, this switching state, plus plus plus, means all the three top switches are on. When all the three top switches are on, your load is shorted through these top switches. There is no energy transfer between source and load. So this switching state is also called zero switching state. Whereas all other switching states, minus plus minus, minus plus plus, plus minus minus, plus minus plus, and plus plus minus, they are called active switching states, because in these switching states your load is connected to the source and there is energy always flowing from source to load. There is the transfer of energy between source and load. So out of these 8 switching states, 6 switching states which I have shown here, they are called active switching states, and 2 switching states, minus 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 and plus plus plus, they are called zero switching states. Why they are called zero switching states? Because they short the load and there is no transfer of energy between source and load in these switching states. Whereas in active switching states, there is transfer of energy from source to load, between source and load. That's why they are called active switching states. So therefore, my inverter is having 6 switching states. Now, let us try to visualize the switching states, with the help of a diagram. So let me first of all see my switching states. I can show you these switching states like this. This is my R phase. This is R phase. So for example, this is my Y phase. And this is B phase. So along R phase, my switching state will be like plus minus minus. Why I am writing plus minus minus? Because along this R phase axis, the R phase voltage will be at its maximum value. So I will put plus here, and other two voltages will be negative at that time. Let us go to Y phase. Along Y phase, which voltage will be at its maximum value? Y. So this is my R, this is Y, this is B. So my switching state will be minus plus minus. I am putting plus along Y because Y phase voltage will be at its maximum value. So this is another switching state, minus plus minus, because I am along Y phase axis, and along Y phase axis this voltage Vy will be at its maximum value. What about B phase axis? Along B phase axis, this voltage Vb will be maximum and other two voltages will be negative. This will be maximum positive and these will be some negative value. So this will be minus minus B. So these are my 3 switching states. Along R phase, I am putting plus along R and minus minus, because along R phase the VR voltage, phase voltage VRN will be at its maximum value. So plus minus minus. Along Y phase, phase voltage VYN will be at its maximum value. So minus plus minus. And along B phase, phase voltage VBN will be at its maximum value, minus minus plus. So if this is R phase, what will be this? This will be negative of this. So if this is plus minus minus, iska opposite kya hai? It will be minus plus plus. This will be minus R phase axis. So if it is plus Y phase axis, this will be minus Y phase axis. Here it will be plus minus plus. Minus Y phase axis means here along Y phase VYN is maximum positive, and along minus Y phase axis VYN is maximum negative. Okay. Similarly, if this is B phase, this is B minus B phase, minus minus plus, so it will be plus plus minus. This is how you show these switching states. And so 1, 2, 3, 4, 5, 6. And you have two more switching states. One is minus, minus, minus. Another is plus, plus, plus. I will put them here. Let me give them some name. This first switching state, let us call this V1. Second switching state is this. Let us call this V2. Third switching state is this. Let us call this switching state as voltage vector V3. This is fourth switching state V4. This is fifth switching state V5. This is sixth switching state V6. This is seventh switching state V7, which is minus, minus, minus. I am showing it on the origin because it does not result. I have already told you when all the three bottom switches are on, load is not connected to source. So load voltage is 0. Load is shorted by bottom switches. So it is to be shown along the origin. Or when top switches are on. So your load is connected to the top switch. It is shorted by the top switches and load voltage is again 0. So let me call this V0 and this as V7 plus, plus, plus. So how many states are there? Switching states 1, 2, 3, 4, 5, 6. These 6 switching states are active switching states, which I have just few moments back shown you in that table. And these 2 switching states, which are at the origin, are 0 switching states. Now each switching state will produce a vector, voltage vector. Let us see how. Let us take switching state V1. Let us take, I will write here, switching state V1, which is given by plus, minus, minus. Okay, it gives rise to a three-phase, voltage, three-phase pole voltages, three-phase line voltage, three-phase phase voltage. This switching state, because R phase S1 top switches on and bottom phase. So R phase top switches on and Y and B phase bottom switches are on. So you will get some three-phase voltage along the load. So I don't want to work in terms of three-phase quantities. I want to work in terms of two-phase quantities in alpha beta reference frame. This is my alpha, this is my beta. For example, ये मेरा alpha है और ये beta है. I want to work in alpha beta reference frame. So just few moments back, we have written V alpha equal to, what was V alpha equal to? That was probably 1 by 2 times 2 VRO minus VYO minus VBO. Let me check it. Was it? Yeah. And V beta was equal to root 3 by 2 times VYO minus VBO. Let us find, the components of, when this switching state is there will be three-phase voltages impressed across the load. Let us transform those three-phase voltages into equivalent alpha beta two-phase voltages and find alpha component of voltage and beta component of voltage. Okay. Now this alpha component of voltage is given by V alpha equal to 1 by 2 times 2 VRO minus VYO minus VBO. So that is equal to 1 by 2 times 2 VRO. VRO means pole voltage of phase leg R. That will be determined whether top switches are on or bottom switches on. What is the switching state? Plus, plus, plus. This is R, this is Y, and this is B. That means R phase plus means iska top switch on hai, S1 is on. And when S1 is on, your pole voltage VRO is plus VDC by 2. So VRO is VDC by 2 minus VYO. What is VYO? Y ka sign kya hai yahan? Minus. That means Y phase ka bottom switch on hai. Minus means iska bottom switch S6 on hai. So what will be VYO pole voltage? Since bottom switch is on, VYO will be minus VDC by 2. Chunki ye already minus hai, minus into minus is plus VDC by 2. Fine. And then minus VBO. VBO is the pole voltage of phase leg B. And it is minus. Iska bhi bottom switch S2 on hai. So pole voltage VBO is minus VDC by 2. It is minus already here. Minus into minus is plus VDC by 2. So therefore V alpha in terms of pole voltage will be 1 by 2 times. So 2 or 2 yahan cancel ho jayega. So this is yahan 2 VDC plus VDC plus VDC by 2. LCM agar aap 2 lenge, so it's 1 by 2 times 2 plus 1 plus 1, that's 4 VDC by 2. So 2 to our 4, 2 and 2 goes, it is equal to VDC. So therefore my V alpha comes out to be VDC. So let me write it here. So therefore alpha component of the voltage V alpha is equal to VDC. Okay, so therefore I will have alpha component of voltage whose magnitude is equal to VDC. What about its beta component? So let us try to find out V beta. V beta is root 3 by 2 times V by O minus VBO, right? So that is root 3 by 2 times, what is V by O? It's pole voltage of phase B, phase Y. So Y minus means its bottom switch is on and pole voltage is minus VDC by 2. So it is minus VDC by 2. Minus VBO. B's bottom switch is also on. So its pole voltage is also minus VDC by 2. Minus into minus is plus VDC by 2. So this minus VDC by 2 plus VDC by 2, they add up to 0. So beta, V beta is equal to 0. So therefore beta component, beta ke along, the voltage is 0. So therefore what is the total voltage? So therefore voltage V vector V1, it is equal to under root of V alpha square plus V beta square. And I mean alpha component you know, beta component you know, so resultant voltage vector V1 will be equal to under root of V alpha square plus V beta square. Just few moments back we found that V alpha is VDC, so it is VDC square, and V beta is 0, so I will not write that, so it is VDC. So therefore V1 voltage vector is equal to VDC. So therefore this switching state gives me a vector, a voltage, a phasor, which is along alpha axis and whose amplitude is equal to VDC. So therefore this V1 will be equal to VDC. Iska amplitude VDC ke barabar, and it is along alpha axis, right? Fine. V5, V6. So that was switching state V1. Let us take another switching state. So before I take another switching state, let me show you this. So this is my, ये मेरा V1 है. So V1 is equal to VDC. जो switching state 1 देती है. Which switching state gives that? V1 plus minus minus. It gives a vector along alpha axis. Fine. Let us take second switching state V2, which is plus plus minus. Yes, switching state अब हम लेते हैं. So this switching state will also produce three-phase voltages. Okay. Let us transform those three-phase voltages into two-phase voltages. उसका alpha और beta component निकालते हैं. V alpha is equal to 1 by 2 times 2 VRO minus VYO minus VBO. That is 1 by 2 times 2 into VRO. VRO means our stop switch is on, so it is VDC by 2. Minus VYO. Y का भी top switch on है, so it is minus VDC by 2. And then minus VBO. B का bottom switch on है, its pole voltage is minus VDC by 2, minus into minus is plus VDC by 2. Now this plus VDC by 2 minus VDC by 2, they add up to 0. 2 and 2 goes, so alpha component is VDC by 2. So alpha axis के across along V2 switching state will give a component whose amplitude is VDC by 2. What about its beta component? Beta component is root 3 by 2 times VYO minus VBO, right? So that is root 3 by 2. What is VYO? VYO ये है. It is Y is top switch is on, so it is VDC by 2. Pole voltage VYO is VDC by 2. Minus B का bottom switch on है, its pole voltage is minus VDC by 2. Minus into minus is plus VDC by 2. So what is VDC by 2 plus VDC by 2? That's VDC, that's root 3 by 2 VDC. So therefore V beta is equal to root 3 by 2 VDC. So therefore this second switching state will give alpha component VDC by 2 and beta voltage component root 3 by 2 VDC. So therefore what will be my resultant voltage? So let me call that voltage vector V2, that is under root of V alpha square plus V beta square. So V2 is equal to V alpha क्या है? VDC by 2 whole square plus V beta is root 3 by 2 VDC whole square. So therefore V2 is equal to, this is VDC square by 4 plus 3 by 4 VDC square. See, 3 plus 1 is 4. 4, that is under root of 4 VDC square by 4. 4, so that is equal to VDC. So therefore V2 vector will be equal to, therefore this switching state will produce a vector V2 whose magnitude is also VDC, but it will not be along alpha axis, it will be along this axis, क्योंकि ये switching state ये है. The switching state is plus minus minus. So this plus minus minus, I can draw it again. So therefore this switching state plus minus minus gives a voltage vector VDC जिसका phase which is at 60 degrees with respect to this alpha axis, 60 degrees. Okay. So so it is along this, because this vector V2 voltage vector is produced by plus plus, this is plus plus minus. It is produced by this V2. It is produced by V2 plus plus minus switching state. So it will be along V2 itself. So therefore V2 will be equal to VDC. ठीक है? तो इसका मतलब after 60 degrees, पहले first your switching state is like this. Your voltage vector V1 is VDC. After 60 degrees, it will reach this position. Let me draw all these diagrams. That will make things easy. 3. I have 6 switching states, active switching states. 4. 5 and one more 6th I can draw here. Let me take third switching state now. What is my third switching state? Minus plus minus. My third switching state is V3 minus plus minus. So what is alpha? This will also result in, three-phase voltages whose alpha component, I mean, when I transform those three-phase voltages into two-phase alpha beta reference frame, alpha component of voltage is 1 by 2 into 2 VRO minus VYO minus VBO. That is equal to 1 by 2 into 2 into VRO. So R phase minus है, इसका मतलब bottom switch is on, so it means VRO is minus VDC by 2. So I am writing here minus VYO. Top switch is on, so it is VDC by 2. Minus VBO. Bottom switch is on, so it is plus VDC by 2. So VDC by 2, VDC, they cancel, 2 and 2 cancel. So it is minus VDC by 2, V alpha. So therefore V alpha is minus VDC by 2. I will write here V alpha, alpha component of voltage is minus VDC by 2. What is its beta component? It is root 3 by 2 times VYO minus VBO. That is root 3 by 2. VYO is, this is VDC by 2 because Y top switch is on, minus VBO, bottom switch is on, minus VDC by 2, minus and minus becomes plus. VDC by 2 plus VDC by 2 is VDC, so it is root 3 by 2 VDC. So therefore V beta is equal to root 3 by 2 VDC. So therefore what is the resultant voltage vector? V3. It is equal to under root of V alpha square, which is minus VDC by 2 square plus V beta square, root 3 by 2 VDC square. So this also comes out to be equal to VDC. So therefore this switching state also gives another voltage vector in alpha beta reference frame whose magnitude is VDC and which is along this. So this is my V3 equal to VDC. That means after another 60 degrees, my voltage vector will come here and it will produce certain amount of three-phase voltages, which I will discuss in a minute's time. Okay, so that was about third switching state. Fourth switching state is minus plus plus, minus plus plus. Let us be very quick. So alpha component It will also produce three-phase voltages, and when transforming those three-phase voltages into two-phase voltages, alpha component of voltages 1 by 2 into 2 VRO. VRO is minus VDC by 2. I will write here minus V by O, that is minus VDC by 2, minus VBO, minus VDC by 2, because these are plus plus, that means top switches are on. So that is equal to 1 by 2 into do gaya. So it is minus 4 VDC by 2. 2 are 4, 2 and that is equal to minus VDC. Okay. So therefore alpha component of voltage is minus VDC. So V alpha is equal to minus VDC. Let us quickly find V beta. V beta is root 3 by 2. V by O is VDC by 2 minus VBO. VBO is VDC by 2. So it is equal to 0. So therefore V beta is 0. So therefore what is voltage vector V4? That is under root of V alpha square plus V beta square. That is also equal to VDC. But it will be along this switching state. The switching state is minus plus plus. So yeah, along. So this is my voltage vector V4, which is also equal to VDC, but along this. So this was about fourth switching state. My fifth switching state is this, minus plus plus. So let me quickly find V alpha. V alpha is 1 by 2 times 2 into this bottom switch is on, so pole voltage is minus VDC by 2, minus top switches of both Y and B are on, so minus VDC by 2, minus VDC by 2. So that is equal to 1 by 2, 2 and 2 goes, minus 4 VDC by 2, 2, so that is minus VDC. What about V beta? V beta is root 3 by 2 into VDC by, this is minus plus plus, V by O minus VBO. V by O is this, that is VDC by 2 minus VDC by 2. So that is equal to 0. So therefore V5 is equal to under root of this plus this, that is VDC, because VDC square is VDC. So I will get fifth voltage vector along this. This is V5. इसका भी amplitude VDC के बराबर होगा. And finally, let me take last switching state, V6, which is plus minus plus switching state. So V alpha will be equal to 1 by 2 times 2 VRO, 2 into VDC by 2, and minus this, minus V by O, it's minus into minus plus VDC by 2, and minus VBO is VDC by 2, so it's minus VDC by 2. This and this goes, 2 and 2 goes, so it is VDC by 2. And what about V beta? V beta is root 3 by 2, V by O minus VBO. V by O is minus VDC by 2, and minus VBO is minus VDC by 2. That is minus VDC, that is minus root 3 by 2 VDC. So therefore V6 will be equal to under root of V alpha square plus V beta square. That's under root of VDC square by 4 plus 3 by 4 VDC square. So 3 by 4 plus 1 by 4 is 4, 4 by 4 VDC square, that is again VDC. So V6 is also equal to VDC. So all the switching, but that V6 vector will be placed, this is my V6, VDC. That means this switching state, first switching state, V1 plus minus minus, it will produce a voltage vector V1 equal to VDC. Now what does this voltage vector mean? It does not mean it's the DC quantity here. Its amplitude is equal to VDC, but it actually represents a two-phase quantity whose alpha and beta components we have calculated. And when you transform that two-phase quantity back into three-phase quantity, it will represent three-phase phase voltages. Three-phase pole voltages, three-phase phase voltages, and three-phase line voltages. So V1 actually, this vector actually represents three-phase quantities. I mean, you can represent it in terms of phase voltages or three-phase line voltages. After 60 degrees, because all of these angles are all 60 degrees, 60 plus 60 plus 60 plus 60 plus 60, because total is 360 degrees. After 60 degrees, my switching state changes from plus minus minus to plus plus minus. And when it changes from plus minus minus to plus plus minus, okay, this voltage vector is rotated through 60 degrees. Earlier it was along this axis, along this. Now after 60 degrees it has reached somewhere here. Its amplitude is again equal to VDC, and this V2 equal to VDC again represents three-phase voltages. But those three-phase voltages are along this axis. After another 60 degrees, my voltage vector V3 is equal to VDC. It has rotated again by 60 degrees. After another 60 degrees, my voltage vector becomes V4. It has reached this position. After another 60 degrees, it has reached this position. It is equal to VDC. And after another 60 degrees, my V6 is equal to VDC. It is produced by this switching state. It's along this. So therefore, after every 60 degree interval, the switching state changes, and these switching states are represented equivalently on alpha beta axis by these voltage vectors V1, V2, V3, V4, V5 and V6. And each voltage vector represents basically three-phase voltages. Let us see how these three-phase voltages will look like. In six-step voltage source inverter, we already know our voltages are like this. Like if you take phase voltage VRN, it's like this. Just revise your three-phase six-step voltage source inverter, which we have already discussed, and we have discussed in last semester also, and which I am sure you have discussed in your BTech. This is 1 by 3 VDC. This is amplitude is 2 by 3 VDC. It's again 1 by 3 VDC. This is minus 1 by 3 VDC, and this is minus 2 by 3 VDC. This is phase voltage VRN. What about V by N? V by N is phase voltage V by N is displaced with respect to VRN by 120 degrees. देखिए ये 60 degree interval. This is 60 degree interval. 60. These are all 60 degree intervals. Phase voltage VBN will start from after 120 degrees. 60 plus 60, 120 degrees. तो ये यहाँ से start हो जाएगी. And it will follow the same pattern. This is my phase voltage V by N. And then phase voltage VBN. VBN. It will start after another 120 degrees. Let me draw these projections. ये देखिए 60 plus 60 120 डिग्री, उसका मतलब वो यहाँ से शुरू हो जाएगी. This is my phase voltage VBN. So these are my three phase voltages. Now interestingly, अगर मैं यहाँ से शुरू करूँ, if I start from here, let me take these 60 degree intervals each. Here my VRN is positive, so I will write plus, that was phase leg R is on, V by N is negative, minus, VBN is also negative, minus. So which switching state is this? Isn't it switching state V1? Let me draw that on the side, on this side. Omega T, Omega T, Omega T. I will draw space vector diagram again. So this is V1 plus minus minus. This is V3 minus plus minus. Fine, these are my 6 space vectors. Okay, each space vector is equal to VDC. Okay, if I take this 60-degree interval, in this 60-degree interval, my phase leg R has maximum value, so it is positive. And my phase leg Y and phase leg V, they have negative values. So what is the switching state? Plus minus minus. Plus minus minus means it is switching state V1. The top switch of phase leg R is on and bottom switches of other two phase legs are on. That gives us our phase voltage VRN equal to 2 by 3 VDC and V by N and VBN equal to minus 1 by 3 VDC. Okay? And it remains there for 60-degree interval. 60-degree interval के बाद अभी हमने थोड़ी देर पहले देखा my space vector it jumps from V1 to V2 and my switching state is now plus plus minus. Now let us see whether it is there or not. This is my after 60 degree ये मेरी switching state है. Phase voltage VRN is positive, so R leg plus है. Phase voltage VYN is also positive, so Y leg भी plus है. इसका मतलब Y leg का भी top switch on है. But phase voltage VBN is negative. That means B phase का bottom switch on है. So which switching state is this? Plus plus minus, and that is V2. So it is V2 space vector. Switching state is plus plus minus. Okay. After another 60 degrees, my switching state is now like this. R phase is negative, minus. So I will write here minus. Y phase is positive, plus. And B phase is also negative. So it is minus plus minus. Where is that? Minus plus minus. So it is vector, space vector V3. After another 60 degrees, the switching state is like this. R is negative, minus. Y and B are both positive. So minus plus plus. So that is this V4 switching, V4 space vector. After another 60 degrees, R phase and Y phase both are negative. But B phase is positive. Minus minus plus, so this is space vector V5. After another 60 degrees, R phase is positive, Y and B phase are negative. Plus minus minus, and that is space vector V6. So therefore, agar aap isko, now you have to understand, see, this is the graphical representation of your switching states. Just few moments back, we consider different switching states like plus minus minus plus plus minus. ये सारी active switching states कुछ देर पहले हमने consider की, and we transformed from ABC reference frame to alpha beta reference frame. और alpha beta reference frame में हमने देखा कि V1 switching state results in a vector V1 equal to VDC, which is along alpha axis, and that V1 vector actually represents, वो तो alpha beta है, but alpha beta को जब आप ABC में वापस ट्रांसफॉर्म करेंगे, that will actually, this V1 vector will actually represent three phase voltages. And what is the status of those three phase voltages? This is the status of three phase voltages. अगर आप three phase voltages देखेंगे, VRN at that time will be maximum positive, VYN will be negative, and VBN will be negative. So plus minus minus. So this plus minus minus switching state, or this space vector plus minus minus, which is equal to VDC, it generates three phase voltages with this status: VRN positive, VYN negative, and VBN negative, plus minus minus. So it will be there for 60 degree. 60 degree के बाद हमने देखा क्या हमारा switching state plus plus minus हो जाता है after 60 degrees. और ये switching state हमें space vector V2 दे रहा है, which is also equal to VDC, जिसका amplitude same है as this. And what does this represent? This space vector V2 basically also represents three phase voltages. And three phase voltages वो ये है. So it is plus plus minus, that is R phase is positive, Y phase is also positive, but B phase is negative, plus minus minus. So it represents three phase voltages. And these three phase voltages will be there for 60 degree interval. After another 60 degree, my space vector जो पहले यहाँ था फिर यहाँ, अब वो यहाँ आ जाएगा. And this space vector will represent again three phase voltages जिनका status minus plus minus होगा. Let us see. R phase VRN is negative, VBN is positive, and VRN is negative, VYN is positive, and VBN is again negative, minus plus minus. So it generates three phase voltages which remain there for 60 degree interval. Similarly, after another 60 degree interval, my three phase voltages are like this. After another 60 degree interval, my three phase voltages are like this. After another 60 degree interval, the space vector V6 represent the three phase voltages which are like this: VRN positive, VYN negative, and VBN also negative. So therefore each space vector, so space vector starts from V1, after 60 degree it is equal to V2, after another 60 degree it is equal to V3, after another 60 degree it is equal to V4, after another 60 degree it is equal to V5, after another 60 degree it is equal to V6, और इस तरह एक cycle complete हो जाता है. That means in a cycle of 360 degrees my space vectors are like this. First it is V1 equal to VDC, it remains there for 60 degrees. After 60 degrees it jumps to this state, it is V2 equal to VDC. After another 60 degrees it jumps to this position, V3 equal to VDC. After another 60 degrees it becomes V4 equal to VDC. After another 60 degrees it becomes V5 equal to VDC. After another 60 degrees it becomes V6 equal to VDC. और इस तरह से एक cycle complete हो जाता है. And when one cycle is completed, these space vectors basically, whether it is V1, V2, V3, V4, V5, V6, they basically represent a set of three phase voltages, and these are those three phase voltages. V1 space vector will generate this set of three phase voltages: VRN positive, VBN negative, VYN negative, and VBN also negative. And this voltage will remain there for 60 degree. After 60 degree, हमने थोड़ी देर पहले देखा, my space vector jumps from V1 to V2, ये यहाँ आ जाता है. And when jumps to this, my inverter output voltage is now changed. Now VRN is positive, VYN is also positive, VBN is negative. So plus, plus, minus, and like that. So that means these six space vectors, which are first here, then after 60 degree reach this, after 60 degree reach this, it produces a set of three phase voltages, which are three phase 6-step voltages. Okay. तो अगर आप इस पे दिखाएंगे, if you show it on but I don't want three phase 6-step voltages. PWM voltage source inverter का मकसद होता है कि हमारी voltages sinusoidal हो जाए. तो उस केस में I should have this type of voltage, say VA या VRN should be like this, sinusoidal. VYN ये है, ये भी sinusoidal होनी चाहिए, not 6-step. And VBN भी sinusoidal होनी चाहिए, VBN. My actual phase voltages, I want that these should become sinusoidal. अगर मेरे space vectors ऐसे घूम रहे हैं, V1, then sorry, if my space vectors are moving, say this is plus minus minus, V3 is minus plus minus, V5 is minus minus plus, so this is V2 plus plus minus, this is V4 minus plus plus, this is V6 plus minus plus. When my voltage vector is here, it produces three phase voltage, जिसमें R phase maximum peak पे है. अभी आपने थोड़ी देर पहले देखा, R phase is having maximum value 2/3 VDC, Y and B are having negative values -1/3 VDC. So that is represented by this instant. तो ये मेरा space vector 1 है, SV1, which is plus minus minus. क्योंकि यहाँ पे आप देख सकते हैं instantaneous value of phase voltage VRN is positive, maximum positive. Whereas VYN and VBN, they are negative. So this represents this state. उसके बाद after 60 degrees, your space vector jumps from V1 to V2. What is the switching state? Plus, plus, minus. That means VRN voltage positive है, VYN भी positive है, but VBN negative है, और in fact maximum negative होनी चाहिए. ये 60 डिग्री के बाद है. ये देखिए, इसके बाद ये 30 plus 30 60 डिग्री आप यहाँ पे पहुंच रहे हैं. और यहाँ पे आप देख सकते हैं VBN मैक्सिमम नेगेटिव है, जबकि VRN एंड VYN आर पॉजिटिव, एंड दैट वो इसके साथ कोइंसाइड हो जाता है. VRN is positive, you can see here VRN is positive, VYN is also positive, but VBN should be maximum negative, और ये देखिए VBN maximum negative है. तो this gives me space vector SV2, and what is the switching state? Plus plus minus. अब 60 डिग्री के बाद आगे चलिए, 30 plus 30 60, ये मेरा नेक्स्ट 60 डिग्री इंटरवल है. So this will give me space vector 3. ये मेरा स्पेस वेक्टर 1 है, ये मेरा स्पेस वेक्टर 2 है, ये स्पेस वेक्टर 3. स्पेस वेक्टर 3 की स्विचिंग स्टेट क्या है? माइनस प्लस माइनस. दैट मीन्स आर फेज नेगेटिव, वाई फेज मैक्सिमम पॉजिटिव एंड बी फेज नेगेटिव. ये देखिए, आर फेज नेगेटिव है, वाई फेज इज मैक्सिमम पॉजिटिव, बी फेज इज नेगेटिव. सो दिस इज सेम एज माइनस प्लस माइनस. ये स्पेस वेक्टर 3 मुझे यहाँ मिलता है. आफ्टर अनदर 60 डिग्रीज, दैट मीन्स 30 प्लस 30 60 डिग्री, यहाँ जब आप पहुँचेंगे you will get space vector 4. और space vector 4 का switching state क्या है? माइनस प्लस प्लस. That means R phase is maximum negative. ये आप देख सकते हैं, R phase is maximum negative and Y and B phases are positive. Y and B phases are positive and switching state is minus plus plus. After another 60 degrees, 30 plus 30 60 degree, you are here. So this will give you space vector 5 here. And space vector 5's switching state is minus minus plus. So R phase is negative, Y phase is negative, B phase is maximum positive. You can see B phase is maximum positive, whereas R and Y phases are negative. So minus minus plus. उसके बाद last switching vector आपका ये आएगा after another 60 degrees, space vector 6. Space vector 6 में R phase is positive, B phase is also positive, but Y phase is maximum negative. You can see Y phase is maximum negative, whereas R and Y phases are positive. So it is plus minus plus. तो ये मेरे 6 space vectors हैं जो मैं 3 phase sinusoidal voltage पे दिखाता हूँ. These are instantaneous values. When space vector, when you are, when our space vector is V1 equal to VDC. On this 3-phase sinusoidal voltage, it represents this instant. जिस instant पे VRN की voltage maximum positive होगी, ये देखिए positive, VYN और VBN negative होंगे, right? Then after 60 degrees आपका space vector V1 से V2 jump करेगा, जो हमने थोड़ी देर पहले देखा, and it represents this switching state. और इस switching state में R phase positive है. यहाँ previously R phase was maximum positive, here R phase will be positive. So for example, here it may be 2/3 VDC, here it is 1/3 VDC, और ये 1/3 VDC रहेगा. Let us concentrate only on R phase. After another 60 degrees आपका space vector अब यहाँ jump करेगा, and that space vector is equal to VDC. That basically represents instantaneous values of 3-phase voltages, phase voltages, जिसमें R phase का value अब negative होगा. अब आप देख सकते हैं ये R phase 60 डिग्री के बाद ये देखिए नेगेटिव हो रहा है. सो इट विल कम डाउन, इट इज माइनस 1/3 VDC, और 60 डिग्री तक है माइनस 1/3 VDC ही रहेगा. देन आफ्टर ये 60 डिग्री, आफ्टर 60 डिग्री योर स्पेस वेक्टर विल जंप टू V4. V4 में R phase फिर से नेगेटिव है, बट इट इज मैक्सिमम नेगेटिव. यू कैन सी, तो ये आपका R phase मैक्सिमम नेगेटिव, ये मैक्सिमम नेगेटिव पे जाएगा और 60 डिग्री तक मैक्सिमम नेगेटिव ही रहेगा. उसके बाद योर स्पेस वेक्टर आफ्टर 60 डिग्रीज विल जंप टू V5. V5 में आपका R phase फिर से नेगेटिव है, लेकिन मैक्सिमम नेगेटिव नहीं होगा. ये देखिए, इसमें आपका R phase फिर से नेगेटिव है, बट नॉट मैक्सिमम नेगेटिव. इट इज मे बी माइनस 1/3 VDC, एंड इट विल रिमेन माइनस 1/3 VDC फॉर नेक्स्ट 60 डिग्री इंटरवल. उसके बाद V6 आपका स्पेस वेक्टर यहाँ जंप करेगा, एंड हेयर R phase इज पॉजिटिव. यहाँ आप देख सकते हैं ये R phase पॉजिटिव हो रहा है, फिर 60 डिग्री तक पॉजिटिव रहता है. इसका मतलब प्रीवियसली भी ऐसे था, लाइक दिस. सो दिस इज हाउ 3-phase, अगर आपकी this is a set of 3-phase sinusoidal voltages, but these space vectors which are earlier V1, then after 60 degree jumps to V2, after 60 degree jumps to V3, V4, V5, V6. इस पे मैंने देखा है कि instantaneous value of phase voltages क्या है. For example, when space vector is here, V1 is equal to VDC, it represents 3-phase voltages, जिसमें VRN का maximum value है, VYN और VBN negative है, I mean some negative. You can draw those VYN and VBN also on the same waveform or separately. So therefore, this represents a set of 3-phase voltages. So VRN is positive and VYN and VBN are some negative values, say minus 1/3 VDC and minus 1/3 VDC. This remains there for 60 degrees. So for example, ये VYN है minus 1/3 VDC. उसके बाद आपकी VYN कहाँ जाती है? VYN आपकी अगर आप देखेंगे ये ऊपर जाए प्लस 1/3 VDC। तो आई मीन आप इसी पे ड्रा कर सकते हो या अलग ड्रा कर सकते हो, VYN भी और VBN भी आप इसी पे ड्रा कर सकते हो या अलग ड्रा कर सकते हो। So each space vector on your three-phase sinusoidal voltage waveforms represents instantaneous value of three-phase voltages VRN, VYN, VBN. Or instead of moving sinusoidally like this, होता क्या है 6-step voltage source inverter में they remain constant. For example, VRN is plus 2/3 VDC for 60-degree interval, it remains 2/3 VDC. उसके बाद आपका space vector जब V2 पे आ जाता है, so इसका value 1/3 VDC पे आ जाता है and it remains 1/3. It does not go like this sinusoidally. It remains 1/3 VDC for next 60-degree interval. And then your space vector after 60 degree becomes V3 equal to VDC. It jumps from this to this position, and that represents your VRN equal to minus 1/3 VDC, and it remains minus 1/3 VDC. And it remains minus 2/3 VDC, then minus 1/3 VDC, and this completes one cycle. जब ये स्पेस वेक्टर V1 से V1 वापस आ जाता है, it completes one cycle of your phase voltages VRN, VYN and VBN. Okay, so I hope this is clear. But our aim is not to produce these 6-step voltage waveforms. Our aim is to produce voltage vectors which are not jumping from V1 to V2, V2 to V3 and so on after every 60-degree interval, because these voltage space vectors, when they jump like this, they produce 6-step voltage source, 6-step voltage waveform VRN, VYN, VBN, as shown here or as shown previously. We want that our voltage should not be 6-step like this, it should be sinusoidal like this, VRN, VYN and VBN as shown. How to do that? For that purpose, our space vectors should not be like this. They should not be, our space vector should not be here for 60 degrees. Then it should not after 60-degree jump to V2. Then after another 60 degree, it should not jump to V3, V4, V5, V6. It should be a rotating space vector, just like three-phase induction motor में rotating magnetic field एक circular path trace करता है. This voltage vector should also be rotating continuously within this circle. It should trace this circular path, circular trajectory, and that will represent my three-phase sinusoidal voltages VRN, VYN, VBN. How to produce that rotating space vector? We'll discuss that inshallah in next class. So this is the space vector PWM is really, it's very interesting, but simultaneously it is conceptual. You have to understand, you have to sit, you have to draw these waveforms, you have to listen to my lecture carefully. Maybe you have to listen to my lecture more than once. You have to understand each and every point, and you have to conceptualize the concept of this space vector. Okay? Once you have understood what this space vector means, then only you can understand space vector pulse width modulation technique, SVPWM technique. So today we have generated space vector, but we have not generated a rotating space vector. We have generated a stepped space vector, which is here for 60 degrees, then jumps here after 60 degrees, jumps here after 60 degrees, and completes one cycle. And that produces 6-step three-phase voltages, VRN, VYN, VBN. In order to produce sinusoidal voltages, I should have a space vector which is continuously rotating in a circle, just like your air gap magnetic field, which is rotating continuously in a machine. Okay, so how to generate that rotating space vector, we'll discuss in next class. I advise all of you to go through this lecture, and you will really find this space vector PWM technique very, very interesting. The concept is very interesting. So provided you take interest, you try to learn. In case of any doubts, any queries, put your queries on the WhatsApp group and feel free to ask me the queries. Thank you.